Hello mathematicians, we're now going to take a look at the properties of the hyperbola. Now this section mirrors that of the ellipse, so I'm not going to go through the whole process of the derivation because for most of the properties there isn't any difference in the process of derivation. So if we tend to point out the results more than anything and have a look at what the property looks like in terms of the diagram, that will be the extent of our preparation for this. First of all, the equation of the chord of contact of a hyperbola we notice is given by this, which, just as in the case of the ellipse, we noticed was essentially the equation of the, in this case the hyperbola, with one of the x values replaced by with the x value and the y value replaced by the coordinates of the point of intersection of the two tangents. So once we get our head around that, what we might notice is a pattern that appears right throughout these equations that we'll work on. And that is that all of these equations are simply those of the ellipse, but with a minus b squared. So not minus b all squared, but b squared with a negative sign in the front. So if you thought about our equation for the chord of contact of the hyperbola, of the ellipse, it would have been this equation with a positive sign there. So we've replaced this b squared by a negative b squared and obtained the equation of the chord of contact of the hyperbola from that of the ellipse. Now, we might just have a look at the chord of contact on GeoGebra. Now, before we actually worry about the chord of contact, we might revisit one of the earlier properties of the ellipse, of the hyperbola, where we looked at the value of a and b. Like, this is a slightly different form of the program, so I'm altering a and b and calculating the eccentricity as a result. So when a is a greater value than b, so the value under the x squared is greater than the value under the y squared, our branches of the hyperbola are sort of compressed vertically. They're squashed down from top and bottom. But if I take a to be less than b, so I'll shuffle this here and shuffle this one up, then my branches of the hyperbola are compressed horizontally. So it looks like it's being squashed from left and right. So you might, and of course the directrices and foci are in slightly different places. So let's just go back to our more usual one. We'll spread it out a little bit. So here we have our two branches of the hyperbola. A is clearly bigger than b, so it looks like it's compressed vertically. We've got our value of e as fairly big, 3.35. We know it's just got to be greater than 1, however. That gives us the equation of this particular hyperbola as x squared on 3.2 squared minus b squared on 1 squared equals 1. From that we can get that the point where we, or the vertex of the branches, are going to be 3.2 and minus 3.2. We can get AE, which is going to be 3.2 multiplied by 3.35, so you can see that's out here. So we can locate the foci. The directrices are A on E and minus A on E, so you can see the position of those. And I'm going to look at the two tangents drawn from this point out here, x1, y1. So if I move that, you can see that we get two different tangents. Now, we can see that this is our chord of contact in here between the 2 points of intersection of the tangents with the branches of the hyperbola. And the equation of that chord of contact would be x, whatever the value of x1 is, on a squared minus y, whatever the value of y1 is, on b squared equals 1. However, just as we found before, if this point of intersection of the two tangents is moved to a directrix, then that focal chord becomes that chord of contact becomes a focal chord. So you can see this dotted line here, so this is the extension of the chord of contact, and it passes through the corresponding focus to the directrix. So if I move it over to this one, for example, then now our chord of contact extended passes through this focus. So exactly the same as for the ellipse. If we have a chord of contact where the point of intersection is on a directrix, it becomes a focal chord, and the converse. If we have a focal chord, then the point of intersection of the two tangents must be on the directrix. So, as I said previously, we won't run through the proof of the chord of contact from a point on the directrix being the focal chord, because we know the shape of that proof from the ellipse. We would actually have to get the equation of the chord of contact, which we can, and then see what the question asks, basically. If we were told that the if we were told that the chord of contact was a focal chord, then we could show that the two tangents must intersect on the directrix. So exactly the same method as previously. I have got a little bit of working here for the difference in focal lengths of a hyperbola, because when we did the ellipse case, it was that the sum of the focal lengths was equal to a constant, and that constant was equal to 2a. In the case of the hyperbola, it's that the difference in the focal lengths of the hyperbola is a constant, and again equal to 2a. The shape of the derivation, however, is exactly the same. So we start by using the definition of eccentricity, and we set up the ratios for both pairs of focal chords and directrices, and then, because we're interested in the difference in the focal lengths, we just work on these algebraically to get that. So these are the two focal lengths. We get that, we plug in the fact that mm dashed is 2a on E, and we get that the difference in the focal lengths is 2a. So let's have a very quick look at that on GeoGebra. So here we can just see our point on one branch of the hyperbola. We could easily do the same over here, and as I move this point along the hyperbola, while the actual focal length varies, the difference between the two focal lengths doesn't change, and the difference between the two focal lengths works out to be 2a. So a is 3.67, the difference is 7.34. If I change the value of a, then obviously the size of the difference changes. It remains at 2a though, and once again, wherever I move the point on the hyperbola, the value stays the same. Now for our next property again, I think it's just knowing what it looks like on the diagram, which is the key part. So the part of the tangent between the point of contact and the directrix subtends a right angle at the corresponding focus. So here we have the point of contact of the tangent, so the black line is the tangent. The part of the tangent between the point of contact and the directrix is going to subtend at the focus a right angle. So again, a quick look at GeoGebra. So with GeoGebra we can see that as we move the position of this point of contact, what stays constant is that we have that right angle there. Even if I go over here, we've still got a right angle at the focus. So that's all that we need to know. And in terms of our proof, you remember our process for the ellipse. We need to find the equation of the tangent. We need to find where it intersects the directrix. We need to get an expression for the slope from this point to the focus and from the point of contact to the focus, and hopefully show that the product of those two slopes is -1. Or, alternatively, use Pythagoras to show that we've got a right angle. Now we then have a look at the reflection property for the hyperbola, and just as in the case of the ellipse, it's not nice, but it's an important property. So the reflection property states that the tangent to a hyperbola at point P, so, well, point P is not actually shown on the diagram, but let's presume it's down here somewhere. So the tangent to a hyperbola at a point P is equally inclined to the focal chords through P. So when we look at this diagram here, it's not all that good. Actually, I think we might jump to GeoGebra so we can see it more clearly. So here we have our point of contact and our tangent in black here, and we have the focal chord coming down here. So as I move the point of contact with the ellipse, it's not all that clear there, but a bit more obvious down here, then the angle between the focus and the point of contact and the other focus and the point of contact, the angle between those and the tangent always remains a constant. So the derivation of this, if you flip back to our previous derivation and think about the fact that from this point here where the tangent intersects the directrix in both cases, since that will form a right angle with our segment of the tangent, then we're going to follow exactly the same derivation there. But that will require some time, some paper, some sitting down and running through it. So just jumping back to our original diagram before we leave it, then that angle and that angle, okay, sorry, that angle and that angle, they're going to be equivalent. Doesn't look like it on that diagram, but that's the property we're after. So let's have a look at a question. So, typical question, if the tangent at any point on the hyperbola meets the asymptotes at Q and R, show that P is the midpoint of Q and R. So step one, as always, should be a diagram so we can get our head around what on earth we're working with or towards. So we draw up our hyperbola, here's our point of contact, here's the tangent, and it intersects the asymptotes. And we want to show that P is the midpoint of QR. So just by getting our diagram together, we basically can form up a plan about how to attack this problem. So first thing we have to do is get the equation of the tangent, which we can do. And we're working in parametric form here, so we could try parametric form, even though this is in Cartesian form, but I guess if you prefer one over the other, you could switch. Now, at Q, the tangent, whose equation we've got, intersects the asymptote. So this is the equation of the asymptote. So we substitute that value of y into our equation for the tangent. When we do that, things cancel out nicely, so we get this expression for x. At R, same sort of thing happens. The tangent is going to intersect the other asymptote, which is minus bx on A. Substitute that into the equation of the tangent, and we get that as our x value. Now, we need the points because we're trying to find a midpoint. So at Q, so that's, I've simply labelled that, and it's arbitrary which one we label which. So at Q, if the x value was this, which we defined or derived up above, then y is bx on A, which comes out to be this. Similarly at R, we're going to get that as our y value, and then if we find the midpoint of QR, it's obviously some of the x values on 2, some of the y values on 2, and now it becomes an algebra exercise. What do we do with this bit here? We get a common denominator, which is that, and there's that 2 sitting down the bottom. So once we use that common denominator, our top line becomes this, which cancels down to that, which is a sec theta, which we know is p. And likewise for y, we notice that the negatives mean that we end up just with 2b tan theta on 2, which comes down to b tan theta. So indeed we have the fact that, which I haven't got written here, which I should have, that the midpoint of QR is in fact point P.